Hi guys, I'm Rob and welcome to this, our 12th lesson in the topic of trigonometry. And in the previous lesson we had a look at finding the length of an arc in a circle. This time we're going to have a look at finding the area of a sector. Similar maths, it's the same kind of ideas here, all right? So remember, if I've got a circle like that, if I pick 2 points on the circle, pick a point here and pick a point here, right? That the part of the circumference in between those 2 points, that's an arc. And that's what we dealt with in the previous lesson, how to find the length of an arc and work with the length of an arc, all right? If I join these 2 points to the center of the circle, that this shape here, that pizza slice shape, that's a sector, right? And I can find the area of that sector again by using formulas, all right? So the area of a sector here is what I'm looking for. And like an arc, to find the area of the sector, I need to know this guy here, the angle at the center, and I need to know what the radius is. All right, so I can, if I've got the center, the angle at the center here and the length of the radius, I can use formulas to find how long that arc is or how big this area is. And again, like we had with arcs, where there's a minor arc, a smaller one here, and a major arc, which when added together make up the full circumference of the circle, here I've got a minor sector and a major sector, right? So if somebody if you're trying to divide up a pizza, and somebody makes those 2 cuts there and say, would you like that size of pizza? Say yes and grab this, because that's a pizza slice as well. Grab the major sector there, all right? So you've got a minor and a major sector here, right? And again, the question will make it very clear which of the 2 sectors you're dealing with, all right? But to find those, I need the angle at the center, theta, and the radius, r. And like when we're dealing with arcs in the previous lesson, there are 2 different formulas for finding the area of a sector, depending on whether the angle here is measured in degrees or radians, right? So if it's measured in degrees, the area is given as theta over 360 times pi r squared. Now that's very similar to what we met with arcs in the previous lesson. Because remember, that part of the formula there, pi r squared, is the area of a full circle. So if I worked out what pi r squared is, it's the area of the entire pizza, right? And then by putting this angle here over 360, I'm working out what fraction of the pizza that is. And by multiplying the 2 of them together, I've got the area of this piece here. So again, that's the one we use when theta is in degrees. Okay, if the angle at the center is measured in degrees. Okay, if the angle is measured in radians, the formula is a half r squared theta. So it's a half the radius squared multiplied by that angle there, right? And like we had for in the previous lesson, that those formulas are also on page 9 of the state exams formula booklet. So page 9 again, you can see there's the 2 formulas we met in the previous lesson for finding the length of an arc over here. And here's the 2 area formulas on the right-hand side of the page. Okay, so there's the r squared, pi r squared times theta over 360, okay, when the angle's in degrees. And there's the half r squared theta there, when the angle is in radians. So both of those formulas are on page 9 of your formula booklet, as a reminder. Get the area here. All I need to know is I need to know what the angle there at the center is, either in degrees or radians, and I need to know what the radius is, right? Now, on page 149, just an important little piece of maths there to have in your back pocket. Okay, very useful calculation, right? That if I've got a circle like that, if I draw a straight line, if I put in a straight line that cuts that circle in 2 different places, so if I draw a line like that, that line there is called a secant line. So as opposed to a tangent line. Remember, a tangent line is a line that hits the circle at 1 point only. Just glance at the circle, hits the circle at a single point like that. That's a tangent line, okay? It's a line which hits a circle at only 1 point. But if a line hits a circle at 2 different points, it's a secant line. So that line there is a secant. And this part of the secant here, right? This bit here, the part of the secant that lies inside the circle, that joins the 2 points where the line intersects the circle, that line there, remember, is called a chord. Okay, so that blue line there is a chord. So the whole line is a secant, but the little piece of that line that lies inside the circle is called a chord. It's a point that a line that joins 2 points on the circumference of a circle, right? That's a chord, right? Now, this little piece out here, that area out there, between the chord and the circumference, that's called a segment. And it's a very useful trick to have in your back pocket in trigonometry, how to find the area of a segment. right? So if I was asked to find the area of that piece there, how can I do it? Well, all we've got to do is, as we've kind of met a few times now during these lessons, combine stuff we've met before. Okay, just do stuff we've met before in combination. So if I was to draw in this line here and that line there, right? So just ignore the rest of the circle now for a second. That's not relevant for the moment, okay? So if you ignore that, look at the shape we've got here. That you can see if I ignore that blue line for a moment, so just visualize that blue line, the chord isn't there. So if I remove the chord like that, you can see what we've got there now is we've got a sector. So I can use one of the two formulas we've just referred to find the area of that sector. Okay, so I can find the area of the sector first of all. No problem. Now, if I put this line back in, you can see this bit here is a triangle. And again, a couple of lessons ago, we had a look at how you find the area of a triangle. Okay, so that's not hard to do either. And if I subtract one from the other, if I subtract the triangle from the sector, I'm left with this bit out here. That's my segment. Now, that's an important little calculation because a lot of real-world problems kind of use that trick there. So if you want to find the area of a segment, it's just the area of a sector, take away the area of a triangle. So we're combining two calculations we've already kind of learned how to do. So if we look at the questions there on page 150, it says find the area of each of the following sectors and give your answers in terms of pi. So you can see for the first one here, we have the first sector we've got, it looks like that, right? And again, we're told that O is the center of each sector, which is important because that means that that's a radius there, 4.5, and then that's an angle at the center. So in this case here, to find the area of that sector, that pizza slice, I'm going to use the formula, it's theta over 360 times pi r squared because the angle is measured in degrees, okay? So the area then, it's theta 110 over 360 multiplied by pi r squared times pi times 4.5 squared. And I can just pop that into my calculator and I get 99 pi over 16. And once again, because there's no unit of measurement given here, there's no unit of measurement given in my answer. If that was in centimeters, for example, this would be centimeters squared because it's an area we're finding. It's the same with the second one there. Okay, again, you've got that sector like that. So there's the center O. All right, so the angle at the center is 75 degrees. And the radius is 9 because it goes to the center of the edge. That's 9 there. So the same formula because the angle's in degrees again. So A is equal to 75 over 360. So it's the angle over 360. That's the fraction of a circle we're dealing with there. Times pi times 9 squared. And again, if I put that into my calculator, I get 135 pi over 8. And again, no units of measurement because there's no units of measurement given in my question. So you can see the other two then at the bottom of the page. These two here. The only difference this time is that the angle is in radians. So I'm going to be using the other formula. So there's Pac-Man again, heading off in the wrong direction. All right. So this angle here is 19 pi over 14. I know that's a radian measurement because there's no degree symbol. Not because there's a pi in there necessarily, okay, but because there's no degree symbol. And because we're told that that's the center point there, O, then that means this 5.6 is a radius. So then it's a half, remember the area when it's in radians is a half r squared theta. So the area here is a half r squared is 5.6 squared times theta, just times 19 pi over 14. Okay, so it's a half the radius squared times the angle. Half r squared theta. And if you put that into your calculator, it's coming out at 532 pi over 25. That's my area. Again, no units of measurement because there's no units of measurement given for the radius. And the last one there. Okay, this little pizza slice here. So again, that's the center O. This is 3 pi over 10. Okay, that's the angle at the center because O is the center. And that means 7.5 here. That's a radius. Okay, so the area there, it's just a half r squared, 7.5 squared times the angle times 3 pi over 10 times theta. All right, and that comes out at 135 pi over 60. Okay, so that's how we apply those formulas for finding the area, okay, depending on whether the angle is given degrees or radians. So if we look at the question then on page 151, it looks like this. It says the diagram below shows a sector of a circle with radius 27 and center O. So O is the center down here, all right, so 27 is the radius. And we're asked to find, it says the area of the sector is 1495 centimeters squared. We're asked to find the measure of the angle marked theta in degrees. So we're asked to find the angle here in degrees, okay? So it's that there's the angle theta there. Now, this sector here, remember, that's the bit we're dealing with. We're told that that has an area of 1495 centimeters squared, right? So the angle I'm looking for is not part of this sector here, okay? So I've got two ways I could go about doing that, right? If you think about it, again, always having options. What I could do here is I could use this sector here to find that angle, right? So find this angle out here, call that A. And then by subtracting that from 360, I can find the one I'm looking for. No problem, right? That's one way of doing it. There's another way of doing it, isn't there? What I could do as well, if you think about it, is I could say, well, look, if this whole circle here has a radius of 27, I can find the area of the full circle. It's just pi r squared, pi times 27 squared. That's the full circle. Subtract 1495 from that, and I've got the area of this sector here. And then we can work backwards to find theta that way. So they're both perfectly correct. Doesn't make any difference at all. I'm just going to do it by finding the angle A here for no other reason than I feel like it. Okay, either of those two methods would be just perfectly fine. All right. So again, because we're looking for the angle in degrees, I'm going to use the degree version of the formula. All right. So what that means then is that the angle over A over 360, okay, times pi r squared, pi times 27 squared. That would be how I get the area of this sector here. The angle over 360 multiplied by pi r squared, pi 27 squared, and I know that should equal 1495. We're told the area of that sector is 1495, right? So as usual, I'll remove the fraction first. So I get 360, multiply both sides by 360, right? And when I do that, that'll cancel. And 27 squared is 729, so I get 729 pi. That's what this is, times A is equal to, if I multiply those two numbers together there, I get 538,200. Right? That's just multiplying those numbers. And then divide across by this. Divide by 729 pi. So A then, if you divide by 729 pi, you get 234.999. So that's what, 235 degrees. Okay, so A there is 235 degrees. Now, don't be that guy who gives that as your answer. Okay, because you're not fully there. Remember, that means this angle here is 235. So to find theta, I want to subtract that from a full circle because those two angles together, you can see, make up a full turn, a full circle there. So theta, the angle I'm looking for, is 360 degrees minus 235 degrees, which is 125 degrees. That's the measure. And it might be worth, if you wanted to convince yourself, doing it the other way. Find the area of the full circle, subtract 1495 to find that area there, and then do this working backwards to show you get the 125 out of the way. Remember, you've always got options. So, if we look at the question on page 152, now this is a great little shape, this one here. Very interesting shape that we're dealing with here on page 152. It says in the question there on page 152, the diagram opposite shows a shape called an equilateral arc triangle, also referred to as a rouleau triangle. Okay, so this is a rouleau triangle here. It says to create the shape, 3 arcs are drawn, each having one vertex of an equilateral triangle as its center and passing through the other 2 vertices. So that's a lot of language for what's actually a very simple idea. That essentially what the key thing he's telling you there is that this is an equilateral triangle. Underline that if you're doing a question. The triangle's equilateral, more on that in a second. Okay, what that means is to create this shape here, I put the point of my compass on this corner and then put the pencil there to draw that curved line. So I use this point here to draw that arc. Then put the point of my compass on this corner here to draw that curved line, and the point of my compass on this corner here to draw that curved line. So each of these 3 arcs are formed by having one of the corner points, one of the vertices as the center, and joining the other 2 together, right? So that point's the center of this arc, that point's the center of this arc, and that point's the center of this arc here. Okay, that's what we're being told here. It says, if each side of the triangle is 9 centimeters in length, find the area of the complete shape. Give your answer correct to the nearest centimeter squared. Okay, so we're trying to find the area of the whole shape there. Now, in my head, we're dealing with a compound shape here again. Remember, like we've met in previous lessons, I want to try and pull that apart into smaller shapes I can deal with individually. And in my head here, these 3 bits here are segments. Like we met in the earlier part of that. They're segments. I'll remind you of that now in a second. And we've got a triangle in the middle here. So I think that shape is 1 triangle and 3 segments. Now, what does it mean when he tells me the triangle is equilateral? Well, if the side, that means that this side here is 9, because he tells me the sides are 9, but that means so is that, and so is that. That all three sides there are 9 centimeters. That's what equilateral means, but there's more to it, isn't there? If you're told that a triangle is equilateral, what else that means? Doesn't that mean that if the three sides are the same, it means so are the three angles? As the three angles are the same and they add up to 180, they're all 60. Now that's a big deal. So that's not an assumption. That's why he told me it's an equilateral triangle. These are all 60 here. Okay? So if I want to find the area here, that getting the area of the triangle is not going to be a problem. Right? But if you want to find the area of a segment, okay, this segment out here, that's the maths that we were talking about previously. So if I ignore these two lines here for a moment, just ignore those two lines for a second, okay, and just take that shape on its own, right? So that shape there. So there's your segment down here, right? That's a segment, because you can see that's the center point here. So if I ignore that line there for a moment, this is a pizza slice, a sector, because we were told that that curved line there was drawn with this point here as a center. So it's a sector with an angle of 60 degrees at the center and a radius of 9. So I can get the area of the sector there pretty easily. So I'll do that first. So to get the area of my sector, I'm going to use the theta over 360 version, because this angle, I put the angle in here in degrees. So to get the area of the sector, it's going to be 60 over 360. Okay, times pi r squared times pi times 9 squared. Angle is 60, the radius is 9. And if I pop that into my calculator, it comes out at 27 pi over 2, which I can leave, but because I'm going to be rounding to the nearest centimetre anyway, I'll just give that as a decimal. So it's about 42.4 centimetres squared. Okay, so that's the area of this entire pizza slice here. Okay, it's a sector with an angle of 60 degrees at the centre and a radius of 9. Now, if I put this line back in, it's now, well, now can I find the area of that triangle? Well, notice, if I've got this line here in the radii, isn't that exactly the right information I need to use the area formula half AB sine C, like we met back in lesson 9? Okay, so you can see I've got two sides and the angle in between them. So if I've got the right information to find the area of a sector, I've automatically got the right information to use half AB sine C. I could have used Heron's formula, couldn't I? Because I know all three sides are 9. So 9 plus 9 plus 9 divided by 2 is S. I can use that formula, but I'm just going to use half AB sine C, because I'll always have that information for any sector, if I've got the right information to find that. So to get the area of the triangle then, okay, it's just going to be a half AB sine C, so a half of 9 times sine 60 degrees. And if I put that into my calculator, it comes out as like 81 root 3 over 4, but again, I'll decimalize that, because he wants me to give it the nearest centimetre. So it's 35, or nearest centimetre squared, 35.1 centimetres squared. So the whole sector has an area of 42.4. The triangle bit has an area of 35.1. So subtracting one from the other will give me this segment down here. Okay? So the segment then, the area of the segment is 42.4, take away 35.1, which comes out at 7.3 centimetres squared. Okay? So this bit here is 7.3. Now, it might be worth just taking a second. It might be obvious, it might not. But this sector here, or sorry, this segment here is also 7.3, because all the measurements are the same. And so is that one. So I've got all the information I need now to get the total area. It's three of these, three segments, plus the triangle in the middle, which I found already. So the area is easy to find now. So the total area then, it's going to be 35.1 plus 3 of the segments. 3 times 7.3, and that comes out at 57 even. So it's 57 centimetres squared. Remember, include your units there, and because it's area, it's centimetres squared. But that little calculation there, how you find the area of a sector, of a segment, that's important. You'll see that in quite a few real-world problems. So if you look at our final question then for this lesson, the one on page 153, we've got a diagram that looks like this. It says, a windscreen wiper clears part of the windscreen of a car windscreen as shown below. Okay, so you can see it says the wiper moves in a circular arc through an angle of 105 degrees from its center, and you can see that's marked in the diagram. That angle there is 105 degrees. Okay, and it says from its center O. So again, we're told that O is the center, which means that these guys here are radii, because they go from the center to the edge, and that 105 is an angle at the center. It's important I realize that that's clear. Okay, that I'm not assuming that. So the angle at the center is 105. It says AB is the wiper blade. And the bottom of AB is 22 centimeters from O. So you can see that means that this bit here, okay? So this bit here is 22. It's how far the bottom of the wiper blade is away from the center point O. So that bit there is 22. And it says that the wiper blade itself is 60 centimeters wide. So that means this bit here is 60, which I'm hoping makes it fairly clear that this radius here is 82. So for the two curved lines we have here, this arc here has a radius of 22, and that big one has a radius of 82. Okay, by adding the two together, because that's really all I need to finish the question. All right, so it says find the area of the windscreen cleared by the wiper. So it has to find this area here. Okay, correct the nearest centimeter squared. So I'm hoping that, again, it's a compound shape. You can kind of see what that shape there is. It's the big pizza slice, the one with the radius of 82, take away the smaller one with the radius of 22. So it's just one sector take away another. And again, for both these sectors, I'm going to use the version of the formula where theta is in degrees because the angle given there is 105 degrees. Okay, so if we do the large sector first of all, okay, so if I do the larger sector, so ignore that line there for a moment. Okay, and just take this whole pizza slice here, the whole thing, okay? It has an angle of 105 and a radius of 82. So the area is going to be 105 over 360, so theta over 360, times pi r squared, pi times 82 squared. Okay, and if I put that into my calculator, it comes out about 61.2 centimeters squared. So that's the entire sector here, right? Now, if I then remove this bit from the whole sector, I've got the area I'm looking for. And that bit there is also a sector with the same angle at the center, just has a smaller radius, 22. Okay? So for the smaller sector, the area is going to be the same angle, 105 over 360, times pi by 22 squared. Smaller radius. And that one comes out at 443.5 centimeters squared. So that the area I'm looking for then, the area cleared by the wiper, is just one minus the other. So it's 6161.2, take away 443.5, which is, it's about 5717.7, so that's 5718 centimeters squared, correct to the nearest whole number, to the nearest centimeter squared. Okay, so that's how we find the area of a sector. So what we're just going to do then in the next lesson, just to round up this part of the topic of trigonometry, is have a look at a couple of real-world problems, a bit like this, that get into working with arcs and sectors. So we'll deal with that in the next lesson.